All right, so let's say we have a system of linear equations. So we have, oops, x plus y is equal to, yeah, let's just keep it like this. Is equal to 3. And then 2x minus 9y is equal to 4. What you could do is go ahead and turn this into a table. You have your variables, and then this is going to be your constant. And you have 1, 2 for x, and then 1, negative 9 for y. And your constants on the other side are going to be 3 and 4. Another way you can write this. Okay, so I'm just now watching the video again before finalizing it, and I realized that my camera is in the wrong spot for you to see what I'm about to write. So just pretend that you can see that, and whenever I end up, doing something in this area over here that you can't see because I made a boo-boo, you could try writing ahead and anticipating me, and then later on, when I get to the next step, the next sequence of the step, whatnot, see if what you write matches what I get on the other end. When I went through this already, everything works. And so if you make a mistake, you'll easily be able to see that if you're listening to what I'm saying and what you did on your own does not match up, try listening again and figuring out what the difference is between those two different steps, where you can see and where you can't, and then where you can't and where you can again. But without further ado, you could rewrite what I was just talking about using, let's go ahead and use matrices. So 1, 2, 1, negative 9. Put a bar here because these are your variables, but then these are your constants. You can expand it and stuff, probably, but this is coming from linear algebra, and you may want to wait until linear algebra to do anything more than just this. You could try it. However, that kind of goes outside the bounds of this particular video. What you want to do is you take your original kind of like matrix for your system of equations, your variables, and what's multiplying them, and then you want to turn it into this. 1, 0, 0, 1. And then your first constant, your second constant of the other two systems. Why does this matter? Because the way that these matrices work is that this is x, this is y, this is your c. And so if you can get it down to this, if this is a 0, then it doesn't work. It's a duplicate system and you only have one equation. But what you can now say is, after you get it down to there, is you can say that x is equal to your first constant, and y is equal to c sub 2, your second constant, or constant. So anyways, let's go ahead and solve this linear equation. What you can't, essentially you're treating it as if it's these two equations right here. You can eventually expand this to pretty much infinite systems of equations. You just have to have, if you have two unknown variables, or two variables that you're using, you need two separate equations. If you have one equation, then you set it equal to one of them. And then if you ever get the second variable that is extra, then you can go ahead and solve for whatever x is at that point, because then it's going to be in relation to whatever your second variable is. If you have 50 unknown variables, you need 50 equations in order to be able to solve it. Otherwise, you can get it close to, setting it equal to a different variable. So this, we're going to go ahead and do 1, 2, -9, and 1. Put the bar there so you remember where your ending point is. Put off a bracket. And you have this matrix. Again, the thing about how many unknowns you have are going to be these rows as well as your equations. This is what needs to be a square matrix, where you have 2 by 2 or 3 by 3, 4 by 4, with the noted caveats. And it doesn't matter necessarily the order of the rows. It does become a problem later on in linear algebra. You have to account for it when you shift rows. But if you're doing a system of equations, it would, if you switch this up here from row 2 to row 1, then it's almost as, then it's exactly as if you wrote the equations differently. So row 1 is written down here and row 2 is written up there. And so the best way to get used to this is to remember that this is row 1, this is row 2, and then if you take a multiple of this and add it to that, you can have a new system of equations if you do it the same way that you do on the real system of equations. What I would like to do here is go ahead and start making this into the identity. I want to go from this to having a 1, and I want this to have a 1 in it, and I want this to be a 0, and eventually, as soon as this guy starts becoming, the -9 becomes a 1, then I can take this one out. So I want to have a triangle of just 1s down the square, the diagonal of the square, with 0s. And if I have 0s here, that's fine. If I have anything in here, it doesn't matter, until I start taking whichever this row is and making these 0s. However, that's going to come later. And this is, go ahead and put this back to where it was. So the first thing I want to do is I want to take row 1, multiply it by -2, and add it to row 2. And what I would say is -1 times row 1 plus row 2 is equal to row 2. It's going to be the new row 2. So, you can say new or something like that, and then just keep on doing it like this. And so you have, in the first row, you still have your 1 and your 1, as well as your 3. That stays the same. It has to. You cannot just manipulate this, the row while you're doing this, unless you're making that row a multiple of itself. And then if you take 1 in the first column, multiply it by -2, and add it to the second column, this becomes a 0. If you do it, or in the second row, when you go to the second column, multiply by -2, and add it to the row below, you get -11. And then when you go with the third column, you have 3 multiplied by -2 added to the row below, row 2, and you have 4 minus 6, which is -2. Now, being as row 1 is finished, for now, we need to make it so that that second row has a 1 in that column, in the second column, which is technically the last column because that's our unknown variables. And so what I would say is I'm going to multiply this by -1/11, the reciprocal, and then make an annotation. -1/11 times row 2 is equal to, the row 2 new, which, let's see if I can figure out where there, found my cursor. And so with this, I keep the same first row, and then I go ahead and compute what the second row is going to be. And of course, being as I multiplied by the reciprocal, this is going to be 1. You should definitely check your math to make sure that you're multiplying by the same thing. However, you kind of know what that's going to be. And then going back over here, I'm going to do -2 times -1/11. And obviously it's, it's a little bit easier to do in your head. However, when you start getting into fractions, this can definitely throw this for a loop. And you end up finishing all this stuff, and because you didn't take the time to make sure that you did your math, your arithmetic correct, now you're in a world of hurt because you've already finished it and the numbers do not work. So we're now in this step. We have our diagonal with 1s, with 0s in higher, with 0s in the bottom, and now we want 0s above the diagonal. And so I'm going to take row 2, multiply it by -1, and add it to the row above. So -1 times row 2 plus row 1 is equal to row 1 new. And this, again, it's going to have a fraction in it, but you'll have 1, 0, and then 1 times -1 plus 1 is going to be 0. And now, being as you have the identity matrix on the left side of the bar in the middle, once this step is done, you are done with figuring out what these variables are equal to. And so row 2 stays the same. However, 3 times 11/11, which is going to be 1, that's going to be equal to 33/11. And then 33/11 minus 2 divided by 11, that's equal to 31/11. And that's our number, 33/11. So x is equal to 31/11. I got it right in the work, but messed it up over there. Let's see, eraser. So x is equal to 31/11, and then y is equal to 2/11. And you can check this. X plus y is equal to 31/11 plus 2/11, which is equal to 33/11, which is 3. If you check the constant in the original system of equations, or system of linear equations, it's 3. So that's equal to 3, and I'm pretty sure that's checked. Now on this one, make sure you do your math correctly, otherwise you'll end up where I was before I did this, trying to figure out why I got approximately 4, which I did my arithmetic wrong on 2 times x, but we have 2 times x minus 9 times y, and this is equal to 2 times 31 over 11 minus 9 times 2 over 11. This is going to be equal to 62 over 11 minus 18 over 11. You can do this in your head probably. Of course, if you want to make sure that you don't make a mistake, this isn't a checking phase, so it's not so important necessarily, because you can easily fix your mistake here. Whereas if you made a mistake at the very beginning of trying to solve the system of linear equations, then you'd have to redo everything. But 62 minus 18, you could also use your calculator. It's going to be 8 goes into 12 and gets 4 left over with a, like it turns into 5 or some stuff. And then you got your 1 over here, so 44. I don't like numbers. I like letters and stuff. I'm a math magician. So this is 44 over 11, which is equal to 4. And then our original second system, or our original second equation was 4. So this is good. And so we've shown that x is equal to 31 over 11, and that y is equal to 2 divided by 11 in the system of equations. Any questions? I'm not going to answer them, sorry. Unless you find me and you force me to answer the question, I guess. But this explains the method using just a 2 by 2 system of equations. 2 unknown variables and 2 equations. And to make this look like circuits, you'll have your KCL. You get the inputs, the input currents, you want them all going in, the sum of them, and you want to you want it to equal 0. And so in some random circuit, you have iota sub 0 plus iota sub 1 plus iota sub 2, and then let's say that our voltage, you want the sum of delta voltage rise equal to 0. This is going to be our KVL, Kirchhoff current law, Kirchhoff voltage law. This is going to be for some random first loop, and then when we get to the second loop, go and put that in. And so you have your voltage, because for some reason this thing is already set up to have an input voltage already. And then you have some devices, iota, your current, sub-0, and then a resistor, sub-0. And then you have another resistor on it. Of course, I'm putting in these R0 and R1 for the resistor resistance, but let's just assume that they have something attached to them. So R0 is 2 and R1 is infinity. No, 10. And then have an R3 equal to 5 and an R4 is equal to 6. And the first loop is done. And then you have a second loop. And by Kirchhoff's voltage law, you want the sum of all the delta, or the change in voltage rise. And you want that to be 0. And again, let's say that you have iota sub 1 times resistor 3, and then plus iota sub 2 and resistor 4. And then all of a sudden it meets up with the original voltage because it was in the middle or something. And when you rewrite this, because we'll say that the voltage is given, but the current is not, you would end up having your system of equations looking like this, with the rows showing properly. Normally I would just put the resistors themselves, have something like, for that first voltage law, or the first voltage equation, something like this. But for this video, I'm just going to go ahead and just do the math. But going back to the system of equations, lining it all up, and you can put something here like epsilon for, it's something used for the motor force, or electromotive force. Or you can say, I think it, RMS. I think we get into that, but anyways, so we have, for our first equation in the system, all of them are 1, and then equal to 0 volt, or now this one would be current, but then go ahead and rearrange this. This is going to be R0, a negative R0 minus a R1, which would be minus 2 minus 10, which would be 12. Minus 12. And then that's it. And the second equation, and then we have a voltage on that one. We have a constant. And then for the third equation, we don't have iota sub 0. We have iota sub 1, which is R3, which is 5. And then iota sub 2, which is R4, which is 6. And then this is also equal to, on this side over here, upsilon, which is the voltage. And so if you were to use the method that you would learn in a linear algebra of using a matrix, possibly you learned this in college algebra, not sure, but if you saw matrices, you may have also seen this method, but now you just rewrite the thing into the matrix and go ahead and get to solving it. We're going to go ahead and say that upsilon is equal to 120. And again, using proper row operations as if you're taking the actual system of equation and manipulating it by substitution and elimination. You want to treat it like it is. And eventually you want this to turn into the technically identity matrix, which just ones down the diagonal and then zeros everywhere else in the square row matrix. With whatever originates on the side here. And then once you know what iota sub 0 is, iota sub 1, iota sub 2, then you know that iota sub 1 is C1, that C sub 1, iota sub 2 is equal to, you got to be consistent in your stuff, Brian. What are you doing? Brian, what are you doing? Brian. But let's go and just say this is 0, this is 1, this is 2. But iota sub 0 is equal to C sub 0. Iota sub 1 is equal to C sub 1. And iota sub 2 is equal to C sub 2. And of course, it doesn't have to be all of one particular type of variable. You can have iota sub 1. You can have upsilon for your voltage. And then maybe if you don't know what the resistor is on a certain one, but as long as you have 3 equations, you're good. And whatever else you need over here to figure out these other 3. And that's solving systems of linear equations. And keeping it kind of neat and tidy a little bit without having to go through writing all the x's and y's or iotas and upsilons and all this stuff. As long as you systematize what you're doing, this will work. I'm just not going to give you the linear algebra lecture to prove that it works. What you can do is try doing it, the hard-learned college algebra way, and then try this kind of glimpse into linear algebra. Because engineers should definitely know linear algebra. If you get to a point where the fractions are like going super insane, what you could try and do is go ahead and turn it into fraction. And then so if you have on the right side, wherever, if you end up having like 333,333 divided by 25, and you go and turn it into a decimal format, and I don't know what this number is, so let's go ahead and say it's some other number. And by keeping it like this, if you want to go ahead and take the reciprocal, then just use whatever you have. If you want to make it the negative reciprocal, then you just make it a negative. And by doing the main method and using the little nuances in order to figure out what each variable is equal to, I think that you will find this extremely easy compared to the work of having to do it the standard college algebra way. And this will work up to infinite unknown variables. So if you have 50, if you have 500, the only issue is the paper. Something you can also do is, if you have that matrix, then you can also make a copy of it on your paper, and then whenever you change something, say that you go ahead and divide, or you turn the middle row into something a little bit easier because you had done the reciprocal of 1/12 which is negative 1 over 12. Then you would end up with 1, 0, 0, and then this would turn into, I believe, negative 10. Well, no, I don't. Well, you're multiplying this, so you would cancel out the 12 and you end up with a 10, and then it would turn into negative. And what you could do is, maybe you like this one better because it already has nothing in these ones over here. And then you can just go ahead and change this row up here, and that goes down. And then you go ahead and subtract your new row into the, you multiply by a -1, add it to the row that you just put it into. So then you have just these guys. And then because already 1 in the second column, you can go ahead and multiply that by -5 and add it to this one here. And then that looks like it would actually turn it into 0, 0, 1 in the third column. And that makes it a little bit easier. Of course, you want to make sure that you do your systematic approach to this correctly. Probably a good idea to always keep your first matrix that has the original system of equations in it, and from that point until you finish, whether you go ahead and make a second one to edit and swap out bits as you modify and arrange them. In the middle, if you make a mistake, you probably won't notice it until you're done. And then you check the numbers and it doesn't work. But if you keep on writing it like I did originally to show the method, then you may end up with a lot of paper that you ended up using, finding out that you did it wrong somewhere in the middle, and you're on a quiz and you can't figure out where you made a mistake, and so you just go ahead and say, I'm going to go ahead and redo it. If you can figure out how to use row manipulations on a graphing calculator, you can actually do this a little bit easier. You still have to make sure that you do not make any mistakes. Check what you're doing. Keep your original matrix written somewhere. But if you do the row manipulations, and at least you won't have to worry about making human error mistakes. It would be more noticeable because you multiply the entire row, and you wouldn't be able to clear out like the second column as easily when you're trying to simplify the second row. So if you're doing on a graphing calculator or something handling matrices, then this would definitely be probably the best way to do it instead of trying to make a program to try and figure everything out. Or you can have something that is already built to handle a system of linear equations. Who knows? But this works. And it's a beautiful thing to use because you're just worried about the numbers. And as long as you do a good job of being meticulous, it shall work. And this is solving systems of linear equations using a technique from linear algebra. May the world be your oyster, or whatever somebody would say. Just don't mess up. Don't let bridges fall.